Previously, you were introduced to an example of modeling for explanation, understanding what factors might explain teacher evaluation scores as given by students at the University of Texas, Austin. Let's now consider an example of modeling for prediction. The dataset I'll use is the house sales in King County, USA, available at Kaggle.com. It consists of homes sold near Seattle, Washington in 2014 and 2015. I'll predict the sale price of houses based on their features such as size, as measured by square feet of living space, where 1 square foot is approximately 1/10 of a square meter. Condition, number of bedrooms, year built, and whether it had a view of the waterfront. Just as with the evals dataset, I've included this data in the moderndive package, which I preview using the glimpse function. Observe, there are 21,000 rows representing houses and 21 variables. As before, let's perform an exploratory data analysis, or EDA, of the outcome variable price. Recall the 3 approaches to EDA: looking at the data, visualizations, and summary statistics. Since I've just done the first approach, let's now visualize our data. Just as with the outcome variable score from our explanatory modeling example, let's get a sense of the distribution of our new numerical outcome variable, price, using a histogram. First, let's look at the x-axis tick marks. Since E plus 0.6 means 10 to the 6, or 1 million, we see that a majority of houses are less than $2 million. But why does the x-axis stretch so far to the right? It's because there are a very small number of houses with price closer to 8 million. You say that the variable price is right-skewed, as exhibited by the long right tail. This skew makes it difficult to compare prices of the less expensive houses. Recall that you saw something similar in the Intro to the Tidyverse course, when visualizing the variable country population from the Gapminder dataset. You visualize the relationship between countries' life expectancies and populations using a scatter plot similar to this one. Because the populations of the 2 green dots corresponding to India and China were so large, it was hard to study the relationship for less populated countries. To remedy this, you rescale the x-axis to be on a log 10 scale. Now you can better distinguish points for countries with smaller populations. Furthermore, horizontal intervals on the x-axis now correspond to multiplicative differences instead of additive ones. For example, distances between successive vertical white grid lines correspond to multiplicative increases by a factor of 10. Now I'll do something similar where I log 10 transform price using the mutate function to create a new variable log 10 price. Let's view the effects of this transformation on these 2 variables. Observe in particular the house in the 6th row with price 1.225 million. Since 10 to the 6 is 1 million, its log 10 price is 6.09. Contrast this with all other houses with log 10 price less than 6. I'll treat log 10 price as our new outcome variable. I can do this since log transformations are monotonic, meaning they preserve orderings. So, if house A's price is lower than house B's, then house A's log 10 price will also be lower than house B's log 10 price. Let's take the earlier code to plot our histogram of the original outcome variable, copy, paste, and tweak the code to plot a histogram of the new log 10 transformed outcome variable. Observe that after the transformation, the distribution is much less skewed, and in this case, more symmetric and bell-shaped. although this isn't always necessarily the case. You can now better discriminate between houses at the lower end of the price scale. Now that you've seen a log transformation was warranted for the outcome variable price, let's see if the predictor variable size, as measured by the square feet of living space, warrants a similar transformation.